All right, let me test it and see. Okay, here we go. Okay, let me make sure. That is the wrong chapter, wrong. Okay. All right, so I jump from, hang on, let me get a, there we go. Hang on, let me give me a second to get this. All right. Oops, sorry about that noise. Okay. Okay. So what I do is I move from chapter 12 straight to 15. I'm sorry, 16. If you look at it, that's what we're dealing with throughout the course. Chapter 12 deals with one aspect of that. Chapter 16 deals with another aspect of that. Then 13, 14, and 15 deal with, 13 deals with this side of it, 14 deals with energy, and this deals with impact. So I'm going to go straight to 16 and finish everything here. Now, the same word is used back here if you look back at chapter 12, I believe, let me see if I can find it. If you look at it, I can just move it to the very beginning like that. It's dealing with kinematics of a particle. What we're dealing with now is kinematics of a rigid body. And the difference between a particle and a rigid body is as a particle came through, it doesn't have any rotation. So now a rigid body, you might have something like this, and as it moves, it can move along a line, but 2 points on it can move in different places, meaning the body itself can move this way, but it can also rotate as it's moving. So he talks about this, where you have rectilinear translation, curvilinear translation, where relative to each other, these points don't rotate. And then you got rotation in any particular way. And then you got general plane motion, which is essentially this one and that one combined. Now, the reason you might be interested in something like this is when you're building mechanisms or something and you're looking at rigid bodies. Technically, you have one rigid body. Now, rigid, if something breaks, it's no longer rigid. Like if this snapped in two, the motion of this point pin over here has nothing to do with that motion, where they can fly around. So you have one, you have two, you have three, you have four, and actually you have five. Here, rigid bodies. Now, their motion is interdependent because they are pinned to each other somehow. And that one, of course, is pinned to the ground, and this one's pinned to the ground. So the fact that they are connected together means we can work ourselves from one link to the other, to the other, to the other, and then finally to the last one. So we can work our way down these links and find the acceleration of these. Of course, the first step towards actually doing something, finding an acceleration of something, then you just multiply times the constant and you'll get the forces. And that's what we're interested in, is making sure things don't break. So when you look at it, you're back in a position where you're looking at this, the way things were described, vector to point A that's on the rigid body, and another vector to point B, which is on the same rigid body. And then if you are sitting here staring at B, the only thing you would see is, since the distance between A and B does not increase, decrease, you would see it rotating. So in other words, this has only rotation. So if someone were to be able to tell you this path r sub a as a function of time, and to tell you what the rotation is, then you can determine what B is, the position of B. So he starts with this, just like what we did in the last section. And he tells you that yet. Okay, before you look at this, the body is translating, therefore. So this is a situation where there is no rotation. If there's no rotation, you get that. Now, if we get a rotation, he's basically talking about rotating about a fixed axis. Okay, now this is something that's new to us. Okay, and if you look back, let me make sure the lecture's going okay on the phone. Okay, yeah, it's going okay. So if you think back to what happened early on in your time with this, somebody had an S, and then they decided to write this. And then they decided that they wanted to call it velocity, so they made up a new symbol and called it velocity. So this is kind of, so I'm basically going to make a corollary between this. This is a new symbol somebody came up with. Then somebody decided that you could take two derivatives, and they decided we should call it something else, an acceleration. Well, wait a minute. These are not vectors quite yet. So they made up a new symbol here. Otherwise, you'd be writing S double dot or X double dot or Y double dot everywhere. So what they decided is they decided that, let's just call it AX and AY. Now, if you look back at the book, you'll find something interesting. Although this is the sequence. But what he's done is he said, okay, now I have this. The corollary is, these are similar. Now, I can do this, but why don't I make a new symbol? Just like I did over here, and it's called angular velocity. And it'll be in radians per second. And this was in radians. Usually it can be expressed in degrees, but when you're talking about this, it's convenient to list it as radians. And the reason being is this. You have, like, this is 2 meters in its rigid body. It's going to go all the way around in a circle. How far did it go? What's the distance? That distance is like 2, in this case, maybe I'll go back and call this just R. 2 pi R. Well, what is this 2 pi? That's theta. So if it went the whole way, it would be 2 pi. If it went just halfway, the distance from here along this path to here, so it turns out that this radian has no units. And so if I multiply 2 pi r, 2 pi kind of represents the 2 pi radians, and the r is in, say, feet. So your distance you travel all the way around this circle is 2 pi r. So by listing these as radians, you could easily get the actual velocity, the tangential velocity out of this. If you list it as degrees, you've got to switch it to radians to get that. So here, let's get rid of that. Get back to, okay, so the next thing that he does is he does this, okay? And let's, yes, you can replace it with 2 dots. Hopefully I did that right. Oh. Well, here. that. Let's do that. So forgive me for that. Now he decides to have another term here. And this is listed as radian per second squared. So all he's doing here, when you see these new terms, just think to yourself, well, that was kind of like S. This is kind of like the acceleration, and this is kind of like the velocity. You're just replacing these terms. So you got a theta. In this case, he puts the theta dot here and the theta double dot here. So what does he do? Excuse me. So he talks about this through here and here. And all he's doing is just coming up with a new symbol. This is a universally accepted symbol, and that's kind of accepted everywhere now. And then he comes up with the angular acceleration, which is listed this way. And then, lo and behold, he comes up with this. Now, this term comes from back. Let me see if I can list this out. Okay, it is true that that's the case. Oops. But that's the case. However, I don't know if I have the ability to select the new. Apparently I do. However, apparently I don't. Oh, apparently I do. Okay. However, let's say you had this instead. In other words, I had omega as a function of theta. In other words, say measuring theta from here, and then I found out omega is equal to like 2 theta squared. So essentially I know that speed is a function of theta. So in fact you could take this, and then that's nothing more than omega. So what you end up with is d omega, d theta omega. Well, multiply both sides times d theta, and lo and behold, you get back this term, which is right here, and this term, which is right here. Now, in the previous section, where it was talking about linear acceleration, it was this. And we had something like that in the previous. But if you just think S is to theta, omega, velocity is to omega, and the acceleration is to alpha, you've got all the same ingredients. Then what does he do? He repeats the same thing. Here's what I mean. If you have a constant angular acceleration, this is exactly the equations that we had before, except, think about it in the previous section, except we had v is equal to v naught plus acceleration t. And for here, we had s is equal to s naught plus v naught t plus 1/2 the acceleration t squared. So if you look back in that chapter 12, you'll see exactly those equations. And then of course you'll see that one too, which is less used, but v squared is equal to v naught squared plus 2 acceleration. Now I should put a c here for designated that it's a constant, times s minus s naught. So that you'll find in the previous chapter. All I did is I replaced theta with s, omega with v, and I'm trying to make it alpha, but alpha with acceleration. So you've seen this before. It's just a switch of terms. Now, okay, so when you're talking about rigid things, the thing that happens is that remains constant unless it cracks apart and part of it breaks off, and if it breaks off, it's no longer rigid. So the assumption is nothing's going to break off or fly off of the spinning object. And it turns out, if you look at this, you'll find that the velocity here is a megar, but I think he'll talk about that in a minute, so I probably should wait until I get, oh, well, no, he talks about it, on this page. But it turns out that in a vector sense, this is the case. Now, there's several ways you can look at this, and that is this, okay? This is a bad representation, but if you look at this, here, let's see. First, let me go forward and see if he has a better picture. And I don't see a better picture. Okay. So let's just use this picture. Okay, so here you are, and this will take some thinking about it. You have some omega. Actually, it's spinning here, but if you put an axis and tilted it here, let me go over and do this in one of these. Let's say you had an object that was spinning, and here's the center part of the object. Oops, that didn't quite look right. So there's the part, the outside ring of it. Now, if you get in on it, and you say it's spinning in this way, then if you take your hand and use your right hand rule, that omega, let's just say, let's put numbers to it, is 2, and it's going in this direction. So this is actual vector. Now, if you wanted to come away from that and make yourself an actual vector, so this is x, this is y, and this is z. So that makes this vector that. Now, if you pick a particular point out here, let's say this point, and you say, I want to find the velocity. Now, according to this, he's telling us this, that the velocity in vector form is omega cross r to the point. Omega cross r to the point P. Let's say that's point P. Your r out to here is this. So if you take your right hand, let's see, I'm not a good hand person, but you take this vector off. In other words, I'm going to take the red vector off. So this is 2k. And then this other vector points out like this, and let's say this is 3j. If you take your thumb, you take your hand, take the points of your hand, rotate them here, your thumb will point this way. Now, that's the direction of the cross, which in fact, you can just take that and put to the tip, the edge, and it turns out that this is going to be nothing more. This velocity is going to be omega, which is 2k crossed with 3j. Now, if you want to be particular and do the way the cross products were taught at one point, you take the first vector and you put in here 0, 0, and 2. You take the second vector and put it in here 0, 3, and 0. Now, if you list them and do the cofactor expansion, I'll take the I times this 0, 2, 3, 2, no, sorry, 0, then minus j, and what I'll do is I'll take this 0, 0, 2, 0, and plus k times this 0, 0, 0, 3, and then what you do is you cross this times that, minus that times that, it gives you nothing. This times that, this times that, nothing. And then you get this times that, minus this times that. So you get minus 6i. So your velocity looks like this. Now, look back at this, and you'll realize that I goes this way. So your velocity is going in the opposite direction, and it's of length 6. Well, the length 6 is just 2 times 3, or the scalar omega, and it's the scalar magnitude of r. So in fact, the reason we do this is because this is incredibly powerful in that it always works. It's a vector representation because it could be that this vector might be in some weird location. In other words, it might be pointing back here. And so if it's pointing back there, it's going to be tangent to its path, meaning it's heading off this direction. And it turns out that in every single case, those are going to be, these are going to be 90 degrees, whoops. Those are going to be 90 degrees to each other. So, cross products are your friend here. Then once he does this, now see what happens to him next is he says, okay, I understand that this is the case. V is equal to omega cross r. But now if I want to find the acceleration, excuse me, cross r plus omega dr d2. Now, turns out that this is actually this. So you get this term, which is just alpha cross r plus omega cross r. Why? Because you put that in. And it turns out this has an interesting approach. If you think about it, it's kind of hard to describe in 2 dimensions, but let's say you had a vector out here. It's rotating, so here's your omega. Here is your r. This is your r. Now, the thing you're supposed to do is you're supposed to do this crossing first. You're supposed to do this first. This vector ends up being right here. So this is the omega cross r. Now, if you take this vector, I'm just going to try to do this in a copying sort of sense. Do a copy and paste. I'll take that vector And then I'm going to cross, take this vector, put right here. If you take your right fingers, you have 5 fingers here, or 4 here, and a thumb here. Here's your thumb. And you rotate or curl those down, your thumb will point this direction. So this will be the direction of omega cross r. But it turns out that that's always in the opposite direction of r. So what he does is he does a thing where he says the minus sign, the magnitude of omega squared, and then the r direction. And you'll see that in here. This is a simplification where he comes through here. He does this, and then he says, hey, wait a minute. So you can read all this, and that's what this is describing. You can pause the video and read it right there if you want to, or if you can go to the page of the book. I'll let it sit there for a second. But it turns out that because of the mathematics, this always equals this. Now, other textbooks will not do this. They will leave it this way. And that's the more rigorous form. But this one has an ability to possibly make it a little simpler in the computation, but even that I'm not really sure I like. Now, I got a few minutes, so what I'm going to do is I'm going to do something really interesting from my perspective, and that's this. I am going to bounce back. Oh, wrong place to bounce. Wait. I am in there. Wait. Hang on. Okay, here's where I want to hit. I'm going to bounce back to 12. Then what I'm going to do, I'm going to slide down to maybe right here. And what I'm going to do, I'm going to show you that this and the other one are actually the same thing. Okay, so I'm just going to copy all of it. I'm going to go back in here. I'm going to drop it right here. And then what I'm going to do is I'm going to go ahead, even though I could just write these equations, I'm going to copy them officially out of the text here. What? Okay, wait a minute. Okay, so I'm going to copy this and drop it right here. And then maybe I won't copy the other one, I'll just write it down. The other one was V is equal to omega cross R. Now, barring this non-existence, because we're not dealing with Z, we're dealing with rotational strings. How does this relate to that? And how does this one relate to that one? Are they the same? Because we've already said this is the case. And we've already said that this is the case. We've replaced these variables. So let's rewrite these two equations with that embedded. So velocity is equal to, I don't have anything here. There's no change in symbol there, and we'll find out why in a minute. acceleration is nothing more than r double dot. Again, I'm copying this, but I'm changing the variable from theta dot gets changed to omega. There's a double dot gets changed to alpha. R alpha plus 2 r dot theta dot, that gets changed to omega. Now the question is, how does this relate to this? Let's start with that one. First, if it's a rigid body, then the distance between 2 points does not change unless the item breaks. Therefore, r dot is equal to r double dot is equal to 0. So I can go ahead, oops, I meant to change colors. It's not behaving. Anyway, I changed colors there. I won't change colors. So now this equation reduces to velocity is equal to r omega u theta, and acceleration is equal to minus r omega squared ur plus r alpha. Remember, that goes to 0, that goes to 0, and that goes to 0. And so I'm copying this right there. I copied that right here. And then there wasn't anything to copy right there. So now let's look again. We got this equation compared with this equation. In fact, if you look at it, the direction, if you look back at the thing, the direction of omega cross r is in fact in the direction of u theta. In other words, this is the direction. You have to remember, when we were doing polar, we had a base vector here, ur, and you had a base vector going up here, u theta. In fact, that base vector, even if you rotate it around, meaning you had a disk, it was spinning about some axis, and you were over here, this would be ur, this would be u theta. So they track each other. So in fact, this is a fact, that the direction of that is the direction, not the actual value. Direction is in the same direction as this. So if you look at that real close, you'll realize those are in fact equal. Those are the same thing. So this is the same thing as that. Now, if you look at this equation, you've got this new equation, acceleration is equal to alpha cross r minus omega squared r. And I got that from right here. I just copied that down here. Now, if you stare at this, you'll realize, hey, wait a minute. That and that are the same thing. So, in other words, alpha, you take a disk, say, it's spinning about some axis here. You take some point here. This is ur. This is the direction of u theta. You take the alpha, which is represented as this. Here's your alpha. It spins here. You cross that with r, or this vector right here. You will get a vector which goes exactly in that direction. So this points exactly in the same direction, and it's actually the exact same value. Now, if you stare at this next one, it's pretty apparent that that And this is going to be the same same exact thing. The vector R right here points in the same direction as the UR. So this points in the same direction as the UR. The scalar value becomes minus. Well, there's a minus here. So in fact, these are both the same thing. So the difference here is this representation is explicitly in polar coordinates. In other words, it's listed like this. These equations, wherever they are, right here, these two equations are in general. They can be in any coordinate system. And we'll see that that has a significant advantage over the previous in that these will work with any coordinate system. They're not focused specifically on polar, but they'll work at all times. And let's see, I'll pop back down to here. So this is the base of it. And what he starts doing now is he starts working in cases in which, okay, you got two gears. The velocity at these 2 points are the same. So then he says, well, what's the speed here? Well, if this is a shorter radius, okay, so V is equal to omega RB, but it's also equal to omega RC. So if these are both equal, and say this one's a little bit smaller than that one, which it looks like visually to me it is, then this omega has to pick up. So in other words, I'm just making up numbers now, but let's say this is 2 and this is 1. Then if this is like 3, then this is going to have this omega over here. So if this thing is spinning at 3, this thing has to spin. Well, maybe I'll make it 4 because I can divide those numbers better. So say it's spinning at 4. If you take the 2 and slide under there, you'll realize this one is spinning at 2. So this one's spinning slower, whereas this one's spinning faster because the radius is different. Okay, then he gives you a bunch of problems related to this. And I don't particularly focus a lot on these, but I may give 1 or 2 in the homework. Then the next thing he does, that's a weird one. That's very bizarre looking. But this is a kind of a standard thing. I don't really have a lot of time, so maybe I'll work that on Monday. Yeah, here I'll put a, you know what I'll do, since that seems interesting, okay, let me go ahead and copy it and work that one Monday. I'll go ahead and put it in its own location. Okay. Here. Wait, come on. That way I'll list it. Okay. I misspelled it, but okay. Here, I'll tell you my work Monday. So the next thing, okay, I really don't have a whole lot of time, but the next thing he talks about is this. And this section is quite a bit difficult because it's a representation that is symbolic. In other words, if you notice, everything is symbolic in the way he represented it. And so this is a set of equations. So to me, if I'm doing that, I'm going to want the symbolic toolbox and something like MATLAB to execute this, because he represents things as a symbolic, and you have to work your way through an equation. That's kind of convenient. and difficult. Then he works into this. And maybe I'll pick this up here. This is where I'll pick it up on Monday and work that problem. So I'm going to go ahead and call it good for right now and drop out of the session here. Wait a minute.